Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process by great poet Rabindranath Tagore, who says, "You cannot cross the sea merely by standing and staring at the water." It is very important statement for all of us who wants to realize their dream and for which one has to work hard and diligently. Let us recall what we learned in the last lecture. In the last lecture, we started discussion on erosive burning and of course, previous to that we had also initiated discussion on erosive burning. And we learned that erosive burning is very important, particularly in the initial phase of the burning when the port area is too small. And erosive burning will be occurring at the aft end, or rather the end portion of the propellant grain, and if the length of the propellant will be increasing, then there is a likelihood of that erosive burning will also be increasing. And when the combustion will be erosive in nature, then naturally there will be increase in the mass of the propellants getting regressed into gas. As a result, there will be increase in pressure, and that can lead to having a thrust. So, therefore, there will be initial increase of thrust provided there will be occurrence of erosive burning. And then after that the burning surface area may not increase much, and then as a result it will be coming labeling to the actual one. And because of that, the total time duration for burning the propellant will be reduced as compared to the case for which it is designed. So, therefore, erosive burning must be avoided or maybe can be minimized. And of course, for that, as I told, one can have a port area to throat area should have been higher than the maybe 4, particularly L by D of 6. And beside this, length of the propellant can be reduced, and we have also seen that if the regression rate is higher, then the erosive burning effect will be minimized. So, therefore, it is important to use the higher regression rate propellant such that the erosive burning can be minimized and its effect can be reduced, as the erosive burning augmentation ratio will be much lower. Keep in mind that this erosive burning augmentation ratio can go up to even 3. So, that is very important point one should keep in mind. After that, we also moved into the effect of the temperature of the propellant on the regression rate. For that, we define a term, and then we looked at how it is important. And later on, we also derived an expression for regression rate by considering a very crude assumption, that is a thermal model, that is by considering the heat balance at the surface of the regression. So, we also derived an expression. We learnt the parameters which can affect the regression rate, and if you recall that we have seen this R dot is basically pressure, chamber pressure power to the m by 2, because it is root. That means, and you can say this is chamber pressure, R dot is proportional to P c. I can say this is N, this is basically your combustion index or the pressure index, whatever you call, and this N will be varying basically something around 0.3 to 0.8, and this is known as the order of reactions. And keep in mind that M is generally N 1 plus N 2, and that is we have already seen for pre-mix flame it will be around something 1.8, and this will be something 1.8 or less than that, and whereas for pre-mix flame and for diffusion flame this will be around something maybe 0.6. This is for diffusion flame. So, this N will be order of that, and one can see that for this double base propellant will be having in this order double dB propellant, and whereas for diffusion flame will be occurring in composite propellant, that will be in this range 0.3 to maybe 0.6 or 7 kind of things. And today we will be discussing about basically how does the chamber pressure in a solid propellant rocket engine will be changing, and it will be dependent on various other parameters like burning surface area and throat area and other things like characteristics velocity. That means, in this case we will be considering the aerodynamics in the port itself. For that we will be making certain assumptions, and the first assumption will be the considering the uniform pressure in the combustion chamber. If I consider a nozzle rocket engine here, and if I consider a propellant surface, let us say this is a end burning propellant and this is my propellant surface areas, and this is end burning propellant, and this area is basically, you can look at, this is your throat area A T, and we are assuming that chamber pressure, if I take this as a control volume like this here, where it will be, this is your control volume, then the gas in this case what will be happening, it will be regressing and the gases will be coming out. This is your gases, gas will be entering with a certain velocity that is V g, and this also will be going out, and we are considering in this chamber that is P c is remaining constant, this is your P c, and all these gases will be obeying the ideal gas, and keeping that the burning rate remains almost constant. Of course, we are considering the end burning propellant grain. So, therefore, that will be burning rate will be remaining almost constant, and we will have to basically do a mass balance. That means, certain amount of gas will be coming out and it is passing through this. Let us say this is the mass flow rate through the nozzle, because this is your throat area A n, and then the mass balance we can consider as a d m by d t, that is the rate of change of mass in the C v control volume will be equal to m dot g, that is the mass of gas generated due to the burning of propellant minus the mass of passing through the throat of the nozzle or passing through the nozzle. So, we can calculate this the mass flow rate of gas being generated due to burning of propellant can be determined as that is your m dot p, and which is equal to the m dot g, and m dot p is nothing but your rho p, that is the density of the propellant. A b is your cross sectional this area, this is your cross sectional area, and r dot is your regression rate. So, we know that r dot is equal to A P C power to the n, this already we have derived. So, if you look at this is nothing but your r dot, right, and A B we know that A B is basically the burning surface area, and rho p is the density of propellant. And the gas flow rate through the nozzle is given by, that is we are assuming that throat to be choked, that means the velocity at this the cross section will be attaining equal to the speed of sound, and we have already derived this expression earlier, that is m dot n is equal to A T P C and C star, and keep in mind that C star is your characteristics velocity that already we have derived, and which is equal to A T P C root over R T C gamma into 2 by divided by gamma plus 1 power to the gamma plus 1 divided by 2 gamma minus 1. Keep in mind that as we are using ideal gas, we can consider certain gamma which will be remaining constant throughout, that means property is not changing along with the length of the combustors, and this portion is we call it basically as a gamma. So, that is the capital gamma. That means, what is saying that mass flow through the nozzle, this is the mass flow rate through the nozzle is basically proportional to the throat area, proportional to the chamber pressure, and inversely proportional to the T power to the half, and also the gamma factors comes into picture. So, if we will strike this balance, I mean if you look at this equation 1, if I say, I mean that itself we can write down and substitute these values, that will be d m by d t, and we know that by ideal gas law, we know that m is nothing but your P v by R T, and R is your specific gas constant, that is R is equal to R u universal gas constant by molecular weight. So, by R T C, and that is nothing but equal to m dot g minus m dot n, and we have already know that m dot g is nothing but rho p a b a p c n, and this already we know this is your m dot n A T P C capital gamma divided by root over R T C. So, what we will do, we will basically expand this term and keeping this temperature remaining constant, and then we can get the expression. Keep in mind that temperature remains almost constant with time, because that depends on the propellant compositions, and it is hardly varies with the increase in or decrease in chamber pressure. So, therefore, that variation we can neglect. So, therefore, that will expand this derivative, that will get, we can take this as a parameter 1 by R T C as a constant, because and then that become V c divided by R T C d P c by d t plus P c by R T C d V c by d t. If you look at this is nothing but your rho g, density of the gas, and dVc by dt is equal to basically change in the volume with respect to time, and that is nothing but your A b r dot, and that is the terms what we are doing, that is rho g and A b, and in place of r dot we are basically writing this is A p c n, and is equal to, this is the term, and this term is basically if you look at m dot g, and this is your m naught n. And if I want to know that how does the chamber pressure changing with respect to time, then we will have to take this portion into the left hand side, this term to the right hand side. I will get and take common of A b A p c n, will get rho p minus rho g bracket minus, this is nothing but your term of the m dot n. That means, the chamber pressure is changing with respect to the A b and then of course, A t. If it is A t is remaining constant, A b may change or may not change. Now, under steady state conditions, when the particularly chamber pressure is not changing, so we can take this term as a 0. So, I will get basically this term is equal to, I can say is equal to 0. So, therefore, this term will be is equal to A b A p c power to the n rho p minus rho g equal to 0. Now, if you consider this, basically if I divide that by this A t p c gamma and root over r t c, right, and you will get basically the p c, that means if I consider that, and you will get this is equal to 1, and I can root over r t c by A t p c gamma. So, this will be cancel it out, and that will be 1, and if you look at this basically you can get this expression as a P c in this term. If you look at, this is nothing but your P c n minus 1, this is a term. So, then if I want to get P c, I can get that is equal to I will get A b by A t, A by gamma and rho p minus rho g divided by gamma root over r t c, because you just take 1 over and 1 over n. If I take this, that will be that you will get very easily. So, you can see this, that is basically P c is a function of, this is known as A r, area ratio, and it is a function of A, and keep in mind that r dot is equal to A P c power to the n, and which is nothing but A by T I minus T p P c power to the n, this is your r dot. So, therefore, it is also a function of T p, that is the propellant gain temperature, and it is also function of chamber temperature or the combustion chamber temperature. And generally you can see that rho p is much higher than the rho g, because of the density of gas will be dependent on the chamber pressure, and however, it will be much lower than the rho p, because rho p is order of something maybe 1800 kg per meter cube, whereas the rho g will be one order at least magnitude lower than that, even lower than that. So, therefore, sometimes this will be neglected as it can be tending towards 0, it is rho g can be neglected, it can be a simplified formula. Now, from this expression you can see that chamber pressure is also a function of n, because this is the term if you look at, and then n is if it is closer to 1, and that become basically very large value 1 over 1 minus n. Therefore, it is very will be problematic. It may lead to the increase in tremendous amount of chamber pressure. It may lead to explosion. So, one has to be very careful about it. So, let us take an example just to see how we can apply this for finding out. So, that is the an end burning rocket employs double waste propellant with a density of 1900 kg per meter cube grain with a diameter of 125 mm, generates around 205 Newton over 215 seconds with characteristics velocity of 1350 meter per second, thrust coefficient of 1.2. The combustion index and burning constant of this propellant are 0.7 and 3.2 millimeter per second for regression rate expression of r dot is equal to A1 P c divided by P r power to the n, and the reference pressure is 7 megapascal in this empirical relationship, and we will have to determine the length of the grain, chamber pressure and throat diameter of the nozzle. So, if you look at the given, what is given is rho p, we know 1900 kg per meter cube and diameter of 125 mm and thrust is 205 Newton, and time duration, time of burning you can say Tb is 215 second. Characteristics velocity is 1350 meter per second and thrust coefficient is 1.2 and n is 0.7 and A1 is 3.2 millimeter per second. And to find is basically length of the grain, chamber pressure and throat diameter, if I say this is throat diameter dt. So, of course, we can get lot of this directly, and let us see how we can do. So, we know that basically we will have to find out what is the length, and for that it is a end burning grain. So, if you look at this is the end burning grain. So, therefore, we know this is the length, we will have to find out this is your length and this surface is basically a B, and for that L is given, diameter is given, this is the diameter of the propellant, D is given, and this is your dt, diameter of this. And we know that F is force is equal to m dot p c star c f. In this case F is given, so we can find out m p is equal to F c star c f is equal to 205 and 1350 into 1.2 is equal to, you will get 0.13 basically kg per second. If you do that, you will get, and the mass of the propellant m p is nothing but your m dot p into T b. So, m dot p is 0.13 kg per second into 215 second. So, I will get something around 27.83 kg of propellant in this engine is being used. So, therefore, from this I can get very easily, because we know this mass of propellant is nothing but rho p pi by 4 d square into L. So, therefore, L I can get m p by rho p pi by 4 d square. If you substitute this value 4 into 27.83, density is 1900 into pi into d, d is your diameter, diameter is something 125 meter. Keep in mind that you will have to convert all the units into same, that is SI unit, you will get in meter, and that happens to be 1.17 meter. And of course, we can find out what is the burning rate very easily. The burning rate R dot, we know L by T B, that is the entire length of the propellant will be burned, and that is 1.17 divided by 215. I will get something 5.43 millimeter per second. And now I need to find out basically chamber pressure. Chamber pressure, we know the expression for chamber pressure by the analysis what we did just now. We can get we know the chamber pressure P c is expressed as A rho p C star A r power to the 1 divided by 1 minus n. Keep in mind that this is if you look at this gamma by root over r t c is and A will be like that. And keep in mind that here we are assuming that rho g is too small, therefore, we are using rho p, and that will be, and we need to find out A, and then rho p is known and C star is known, and A ratio we need to also find out that, right, and we should also find out what is P c. So, then only we can, and the P c we know that P c we can find out very easily, because we know the regression rate, that is R dot is equal to A 1 P c by P r power to the n. So, therefore, we know this regression rate, that is 5.43, and A already we know that is 3.2, and then P c we do not know, reference is megapascals. So, power to the 0.7. So, therefore, I can get P c is basically 14.89 megapascal. From this expression you can get, this is the thing, and by knowing this one I can get basically area ratio from here. It will be P c and power to the 1 minus n divided by A rho p C star, and A I need to find out. A is basically in this expression, as we know this from this expression, that A, and this A is nothing but A 1 divided by P r power to the n, that is the A. So, this A 1 is 3.2 into, that is your reference pressure 7 into 10 power to 6. So, that you can really use here, and then if you substitute these values, you will get the PC is 14.89 power to the 0.3 divided by 32 into 0.7, 7 into 10 power 6, 0.7 into 1900 into your C star is basically 1350 meter per second. So, that you will get this area ratio, you will get, if you do this substitution, you will get something 1069.85, which is very high, and then from this I can get AT, this is AB by AR, and AB I know that pi by 4 d square divided by AR, I will get pi by 4, d is your 0.125 whole square divided by the air 1069.85, and that is happening around something 11.47 10 power to minus 6 meter square. And from this you can get very easily, that is your dt, dt is pi by 4 by pi and at root over. So, if you substitute by this, pi into at is your 11.47 10 power to 6, you will get something around 0.00382 meter, which is equal to 3.82 millimeter. So, this is the thing you got, and this is one answer L, and this is your chamber pressure, this is another answer, and this is your dt. So, by this you can, but there is another very simple way of doing it. Instead of using this complicated formula in this problem particularly, you can get from the basically definition of the characteristics velocity, or even from the your CF, the coefficient of thrust, you can find out. Thank you very much. We will stop over here, and we will look at in the next lecture about the grain design and how to talk about grain. Thank you very much.